Okay, kids, we're in the second video wiring up our home broadcaster, and in these videos I'm trying to keep each one of them somewhat short. I don't want to have these big long videos, and it's easier if we break it up into smaller segments when we're building a project and trying to show progress one step at a time. So here's the piece of masonite that's working as our chassis, and I put a binding post in the middle. This is going to be where our antenna is. Over here I have a microphone jack, and that can be any source. You know, it can be coming from your CD player or your solid state recorder or your smartphone. And I've started the wiring. So I'm trying to follow the book as closely as possible with the wiring. In this video we'll also select the transistors. I do not have genuine General Electric vintage 2N107s, and I wouldn't want to use them in a circuit like this anyway because they're quite collectible. But I do have a wonderful collection of germanium transistors, and many of these are identical to the 107. And you might remember I had a series on germanium that you guys can look up, and you can find out how to build your own testers for these transistors. I'm not going to get too deep into that, but we are going to select some transistors for the circuit. 2N107s are considered to be collector's items at this point, and I'm not going to solder them into a circuit, nor am I going to pay $30 or $40 each for the transistors. But I have quite a nice collection of old germanium transistors of the same era. Some of them are actually out of the old Polypacks kits, and they're truly pitiful examples of germanium transistors. And what I'm going to do is test them to the specifications of the 2N107 so that we have some good representations of transistors. I have the original data sheet from GE over here, and the GE data sheet is, you know, it says things like a noise figure of 22 dB. That seems useful. It's funny, a lot of the specifications that the GE puts in here are not really the ones that an experimenter would have much use for. For instance, the current amplification, the way that they specify it is a little bit unusual. So what we would like to know is HFE, or what is the gain, the current gain of the transistor. So when you look at the data sheet, it doesn't give you that in black and white where you can really understand what you're doing. But later data sheets do give you the pertinent information. And what we find is that the current gain, or the HFE, the worst spec that I found online was 19, and the highest spec I found online was 80. But the typical is 30, and the minimum specification, for instance with a Motorola or a GE later on after the transistor became established, is 20. Also, I saw frequency responses on the transistor specified all over the place, from 300 kilohertz on one data sheet up to 1 megahertz on others. So this really explains what was going on with germanium alloy type transistors in the 50s through the mid-60s. They really didn't have the process completely under control, meaning the distribution was fairly wide, so they had to select transistors for being in the middle of the range, higher than the range, and lower than the range. And the ones that were kind of the fallouts were considered to be hobby transistors. The ones that were really hitting their mark and were very stable, those went into a lot of the military grade systems. So I'm going to grade myself some 2N107 transistors, and we'll use those in the circuit to start. Okay, the first transistor that I stuck in there is around a 43. That's in our range. 80 max, 30 typical, 20 min. So that guy will work. But here's a transistor that has too much gain. 170. I wonder what kind this is. It's a General Electric 2N1175. Okay, so that's a more modern germanium, and it's not going to be a good choice for this because it's too good. Now here's one. It's reading 72 and it's got nice long leads. That might be a good choice. It's a 2N396. Wow, this one's off the chart. A 220 HFE. Another General Electric transistor. It's a 2N508 alpha. Okay, here's an unmarked Polypax transistor. These are the kind that come in the bag with no markings at all. It's got a gain of 36. That's a great choice. That's almost exactly what an early 2N107 would be. Here's another one of those unmarked Polypax jobs with a 63. Another candidate. So we now have 4 transistors selected for current gain. The next thing we should check is to see that the transistors have some actual AC gain that they're actually able to amplify. Now for this test I'm putting out 10 millivolts at 1.7 megahertz, so the top of the AM broadcast band. And it's set for 10 millivolts. And we're going to measure the amount of output we get with 10 millivolts into our a simple amplifier that tests the gain of the transistor. So first I have my Polypax transistor in there, and it looks like I'm getting out about 120 millivolts. 10 millivolts in, 120 millivolts out. So that first transistor gave us about 21 dB of voltage gain. And this guy is considerably lower. The second Polypax transistor is only giving us about 13 or 14 dB of voltage gain. So the long leg black transistor is giving, again, about the same as the first one, or around 21 or 22 dB of gain. So what's the point of checking the gain of the transistors at 1.7 megahertz? Basically, we need to know that we have gain there so that we can use that one transistor as the oscillator circuit. We need to have a gain that's enough to allow the feedback to produce oscillation. And I think these transistors should work okay. We've graded out some fairly poor performance germanium transistors. We know that they have both DC and AC gain in our range, so they should work in the circuit, both for the audio stage and for the RF stage. Okay, kids, if you've been watching, I think we're making some good progress. This is just the parts mounting, and that metal strip up top, which is in the article, is how the variable loop stick attaches securely with its little mounting ears. They don't trust the perf board or the masonite to hold the coil properly. And by the way, looking at the article more closely, I can see that they used old-fashioned perf board made out of either a composite or a FR4 style. This is something that you could have bought at Allied or Radio Shack. I used masonite because I just assumed it was masonite because I looked at the picture very quickly. I've got most of the major parts mounted now. You can see that I have the microphone connector mounted way over here. I wanted to use a real stereo microphone connector. Here's your on-off switch, your battery clip, your oversized terminal strip, which we're going to put the components on. I've added a component up here to hold the antenna. The whip antenna is going to go up from this point. And I've got another little terminal strip just for the center tap of the coil, because my particular coil form did not have a third terminal like they show in the article. So I had to put a solid terminal there for the center tap, or that was definitely going to break. Here's a few pictures from the construction, and these are high enough resolution that I will put them up on the resource page on Facebook, or you can pause and look at these. Just showing some of the techniques for tack soldering the parts onto the terminal strip. So tack soldering is the technique I'm using because this is an unproven circuit, and I know that I'm going to be modifying it. I may be adding resistors, I may be substituting transistors, so I'm not going out of my way to make firm mechanical connections. I took the pictorial diagram that's in the book and I blew it up on my scanner and printed it out so I could see what I was doing. And this is a good technique for beginners to do the wiring. My terminal strip is not exactly like theirs. The one they had actually has places so you can wrap the leads around by sticking it through the middle of the posts. Some of you are a little put back by working with PNP transistors, and especially some of these older circuits that don't seem to look right the way that they're wired. So let's go through the circuit. First of all, where's ground? I don't see a ground symbol at all in the schematic. Where is ground? And with a PNP transistor, the positive is considered the ground on most of the circuits. So if we kind of do a conventional ground symbol, it goes right here. Okay? So the most positive part of the circuit is considered the ground point on the schematic, and it's the positive terminal of the battery. Positive current flow from the battery, you're going from the ground. Okay, now we're talking about positive flow. With positive flow, conventional current, we come out of the positive terminal of the battery, follow the arrows, go up through the second transistor, keep following the DC path, and finally back to the switch and the negative terminal. So that's how current flow goes in this circuit. You can describe it as negative current flow or positive current flow, it doesn't really matter. The other components, these two resistors, are for biasing the transistors. And that's pretty much it on the DC level. On the AC level, this is also ground because this is your microphone. So if you're going to be putting in a source, either a microphone or a CD, or perhaps it's a digital player or a smartphone audio source, it's going to go into this, and of course the positive part of the battery, that's your ground point. So this is where you want your shielded cable, and that's where I've put the little stereo jack, is right here. That will allow us to put in almost any source into the transmitter so we can broadcast music, programming, whatever. So another problem, I wound the coil, and clearly the schematic wants the center tap to be closer to terminal 2 here, which is the feedback to the base. How do I know which lead is which? Well, we wound the coil, so where we started the wind would be the bottom. So look for the lead that's closest to the body of the coil, and that's going to be this bottom one here. Then the center tap is where it is, and of course the one that comes off the outside of the coil is the top. And that's the side that's going to go to the antenna and to the collector of the RF oscillator transistor. The wiring has been completed. We've got the schematic, We've got our pictorial diagram. The only thing we're missing is the transistors. I'm not even going to mount the transistors until I've buzzed out the circuit to this point. So we're going to do that by using the meter with the beeper function. I want to make sure that we understand the schematic and the pictorial and that every wire is where it should be before we go to the next step, which will be mounting the transistors. And I'm going to be tack soldering. Most of this circuit was tack soldered. And by that I mean you don't wrap the wire around the post unless you know that you've got the circuit completely happy and you've worked out all the kinks. So for starters, we're just using solder for the most part. Maybe I just bend the lead so that it makes contact with the terminal strip, but I'm not going as far as to do a proper mechanical connection, because I know if I have to change something, it's going to be a complete mess to undo what I've done. Now, when you're building something like a Heath kit or something that is already validated, go ahead and use the proper mechanical method of soldering, which is to make a good mechanical connection, and then add the solder and heat to complete the connection. So, for instance, let's try the circuit from the antenna terminal to the center tap, okay, because we know that. Okay, so we go from the antenna terminal to the center tap. Okay, so we know that's good through the coil. Also from that point, we should be able to go all the way down to C3, to one side of C3. That would be the other side of the coil. Okay, so that's how we do the buzzing. So again, we're going to the base of the transistor to the switch, and we are reading the 47 or the 48K. So we just measured from this point to this point. So again, we go through the whole circuit, buzz it out. We'll be using the ohm meter when we have resistors in line, and we can use the beeper when we're just testing wires. Now the connection between the emitter of X2 and the collector of X1 is done on this terminal where we have C2. So the two transistors, both leads will complete that circuit. So you can't really buzz that out yet because the transistor's not in line. The horrible Polypax transistors, the poorest examples that I could find in my junk box, are now mounted. And make sure you get the emitters and the collectors in the right position. It was fortunate that I had a terminal strip that had the right number of terminals, so that nothing crazy had to be done. And in the next video, we fire this thing up. Now, Mike, I clearly know my color code. And that resistor that you put in there that's supposed to be a 220K, red, black, yellow, that's 200K. That's not 220. Why are you putting a 200K in there? Well, this brings up another point. I'm going to put our meter across that resistor. Oh my heavens. It's reading 221K. So here lies another issue with building circuits with vintage parts. Sometimes they go out of tolerance because they age. Sometimes they were never in tolerance to begin with. And if you were to stick a 220K in there and it was 25 years old, it might read 300K or 400K, who knows? So that's something you should check. Check your resistors to make sure they're somewhat close to value. We should probably check that 47K while we're at it. 48. Okay, so just keep that in mind, that there is a tolerance and there is aging on some of these old components. It's wired, and in the next video we're going to put this guy on the air, see how it sounds, see if we got the biasing right on those germanium transistors, and hopefully stabilize it. And then finally we will modernize it and use modern silicon transistors. Hope you're enjoying this little series on a kid's home broadcaster.